record. All right, let's talk about graphing logs, day 4, logarithms. So let's make a table to graph this. And the easiest way to graph anything is to make a table. Now, when we make this table here, all right, I'm going to put this in exponential form. All right, remember the log base b of a equals e. All right, so you can remember this as bacon and eggs. In exponential form, it would be b to the e power equals a. Yes, it is around that time to be hungry. So we could take this, the base is 2, the answer is x, and the exponent is y. The reason why I put it in exponential form is because it's way easier to just raise 2 to some power than to take the log of something base 2. So by putting it in this form, we make doing the table easier. But something different about this is that we're actually going to plug in numbers for y and see what x is. So we're going to treat y as our independent variable when normally x is our independent variable. So one number we can plug in for y is an easy number like 1. All right. So if we plug 1 in for y, 2 to the y power is 2. So then when y is 1, x is 2. All right. If we plugged in another y value, 2, just made that up because it's an easy number. I know what 2 squared is, so I'll let y be 2. Then x is 4 because that's 2 squared. All right. And if you were to keep going in that direction, I'm actually going to split this into 2 boxes because I want to go in the other direction. So I'm making an extra thing for the table. If we kept increasing y, so made y 3, then x would also increase because now x is 2 cubed. So x is 8. So as y got bigger, so would x because x is 2 to the y power. So like if y was 10, then x would be 2 to the 10th power, which is a relatively large number. So it's like y approaches infinity, x approaches infinity. So these graphs, as you are going to go up and to the right. What happens as you approach negative infinity for y? So let's take like 0. All right, if we plug in 0 for y, anything to the 0 power is 1. So 2 to the 0 power is also 1. All right, if we were to plug in like negative 1 for y. So now 2 to the negative first power is 1/2 because when you have a negative exponent, it's going to turn into the reciprocal of 2 to whatever that power was. So notice how x doesn't really become negative, but it's getting closer to 0. So like, let's say I plugged in negative 5 for y. So then x would be 2 to the negative 5 power. And I know 2 to the 5th power is 32. 2 times 2 times 2 times 2 times 2 is 32. So 2 to the negative 5th power would be just 1 over 32, or 1 over 2 to the 5th power. So as y approaches negative infinity, x is approaching 0. So that's going to create a vertical asymptote because x is never going to be negative here. So let's sketch the graph first, and then we can answer all these questions. So when I sketch my graph, I'm going to put the y-axis like towards the left of my graph paper, but the x I can put right in the middle. And that's because we're not going to need any part of the graph to the left of the y-axis. So we plot this point, 2, 1, that would be right there. 4, 2, that would be right there. 8, 3, 8, 3. So as x increases, y is increasing, but kind of slowly, but it's going to keep increasing. It will eventually, it'll just keep going up and up and to the right and to the right. But that doesn't happen when you go to the left. It doesn't just keep going down, down, down. Well, it does go down, but it doesn't keep going left, left, left. All right, if we plot this point, 1, 0, that'd be right there. Now, when y is negative 1, x is going to be 1/2. And as y becomes more and more negative, so like when y is negative 5, so 1, 2, 3, 4, 5, x is going to be 1 over 32. And as you plugged in like more negative numbers for y, like towards negative infinity, this graph would just keep getting closer and closer to 0, but would never actually touch 0. So you have like a vertical asymptote at x equals 0. Which means the graph will never reach x equals 0. So it's getting closer and closer to that. Does that make sense? So it's just like an exponential function, except instead of having a horizontal asymptote, it has a vertical asymptote. I actually want to pull up Desmos real quick so we could see the relationship between y equals 2 to the x and y equals the log of x base 2. Oh no, Wi-Fi ain't gonna work. Yeah, I'm gonna say that for sure. Come on, Wi-Fi. All right, I got this. We'll go all audible to, okay, we're here. So y equals 2 to the x power. And then we got also functions. Now I could do this on a T Inspire. I just wanted, I could zoom in more freely with this. As we learned when we first learned about logs, like these two graphs are inverses of each other, which means for every point on y equals 2 to the x, if you were just to switch x and y, that would give you every point on y equals the log of x base 2. So like this point here at 2, 1, that means the inverse is going to have the point 1, 2, and it does. So why do I point that out? Well, that means instead of remembering logs and exponential functions separately, you just remember stuff about exponential functions and understand that they're inverses. So like for example, like this graph goes to the point 0, 1, which means the inverse will go through 1, 0. All right, this graph, as x approaches infinity, y will approach infinity. So if you flip that, all right, when y approaches infinity, x approaches infinity. But on the exponential, as x approaches negative infinity, y is going to level out and get closer and closer to 0, which means it would have a horizontal asymptote at y equals 0. So if you switch x and y, now you have x equals 0. That's a vertical asymptote. That means that this log will have a vertical asymptote at x equals 0. So instead of saying as x approaches negative infinity, y approaches 0, as x approaches 0, y is going to approach negative infinity. And like, it'll never actually hit the y-axis. Like if I just keep zooming in here, it looks like these two things overlap. If I zoom in close enough, they won't. There it is, see? There's a little space there. And if I kept going down and zooming in, you would always find this space in between the y-axis and the graph, because it has a vertical asymptote. Yeah, because like, well, think about it. Like, so take this here, right? So y equals the log of x base 2. That's equivalent to 2 to the y power equals x. So even when like y is like a really big number, so like I was putting 1 million just for a reference, or negative 1 million. So like when y gets really, really far down, like when y is negative 1 million, x is going to be 1 over 2 to the 1 million power, which is still like not 0. It's just very, very close to 0. Yeah, it's like if we had like $1 and we split it with 2 to the 1 million people, which is like way more people than on Earth, everyone would get like a fraction of a penny. Yeah. But there'd always be something. You could divide it up into smaller, smaller pieces. All right. All right, cool. So for logs, the domain is going to be restricted. And it's going to, so we could take this and we could shift it left or right, and it might change the domain for other functions. But for this one, the domain is x has to be less than 0. No, what am I talking about? Liar, I lied. X has to be greater than 0. So x cannot be negative or 0. So you can only plug in positive numbers in for that log. And that's true for all logs. You can only take the log of positive numbers. All right, but the range is unaffected. The range, it does go up and down forever. You could hit any y value. So the range is all real numbers. All right, as x approaches infinity, y keeps going up. So y will approach infinity. And x never approaches negative infinity. So I'm actually going to fix this. I'm going to change it. I'm going to say as x approaches 0. And I'm going to do something that's a little crazy, but I'm going to put a little plus sign up in the exponent. And what that means, because you can approach 0 from the right or the left. So the right would be the positive side. So this means as x approaches 0 from the positive side, y is going to approach negative infinity. But only as you approach 0 from the right side. Now, when you look at increasing and decreasing, you look to see like what's happening to y as you look at the graph from left to right. So when we look at this from left to right, it's going up. So it's increasing. We got an asymptote at x equals 0. So it's a vertical boy. Then the intercept, it only crosses the x-axis right there. So it's at 1, 0. Intercepts are just where x and y are 0. So it's the only time that's going to happen because x can't be 0, but y can. So the intercept is at 1, 0. Okay. So when you graph a log, the first thing you want to do is find the domain. So what did I say about like what you take the log of a few minutes ago? Anyone want to remind me? Like you only take the log of certain types of numbers, or else positive. Very good. Beautiful. So in order to find the domain for this, one way to do it for any log equation, you could just take what's inside the log and say, all right, that has to be positive. So you can only take the log of positive numbers. So you take the expression inside the log, say, hey, I'm taking a log of this, it must be positive. So I'm going to say it's greater than 0. And then you could solve. So the domain of this one would be x is greater than -3. Now let's think about another reason why that makes sense. What happens, what type of transformation is occurring when you compare the log of x base 2 to the log of x plus 3 base 2? Like what happens to a graph when you just add 3 straight to x? Does it move in any certain direction and how many units? Yeah, it moves to the left. So if you take this vertical asymptote and this graph and then shift everything to the left 3, all these points move to the left 3, and so does the vertical asymptote. So this would have a vertical asymptote at x equals 3, -3. Just give you a visual of that. No, actually, let's do this. No, all right, I guess we're doing that. Y equals, where's my little keypad? Functions, logs, log. Oh, that's that up. Log base A, 2, up. All right, so there's that. Now I'm going to do like plus A. Okay, so look, this is what we originally have. We just had the log of x base 2. Now, if I were to add 3, notice what's happening to the graph. It moves to the left 3. If I add -3, it's going to move to the right 3. And I could also show you the asymptote is always going to be at x equals like -A, because that's what, if you set this equal to 0, that would give you the vertical asymptote. So notice how the asymptote moves along with all these points. All right. So for the next one, you can use the same logic. You could say, all right, for number 2, what's the domain of f of x equals a log of 5x, 5 minus 2x? Now, this doesn't have a little number written, which means it's base 10. But the base of the log is not going to affect your asymptote at all. It's just going to affect like the shape of the graph. So if I made this b, come on. Didn't mean to do that. There's no back. Or is it undo? Let's go. Thanks. Thank you. Wait, why is this not? Okay. So notice how, like, look, if I mess with the base, now the base is always going to be greater than 1. But if I mess with the base, like, that intercept is not changing and the asymptote isn't changing. It's just changing the shape of it. So when we're graphing these, like, the base doesn't really affect the graph at all. It's just going to affect the shape of it, which when you're sketching it, you're not going to really see anyway. So it's going to make it more narrow or less narrow. So we could just, when we're looking for the domain, all we have to do is ignore the base, look at what's inside the log, and we know that that has to be positive, which means the domain is going to be x is less than 5/2. And it would have a vertical asymptote at x equals 5/2. So basically when you're graphing these, the first thing you should do is find the domain. Like take the expression inside the log, set it equal to greater than 0, or set it greater than 0, not equal to. Find the domain. Now you know, all right, you're only graphing over these x values. So it's x is less than 5/2. So now it's going to be to the left of 5/2. And you also know that x equals that number is going to be the vertical asymptote. So like, look, if I were to graph this now. No. So I'll make this base 10. I'll go 5 minus 2x. What am I doing? I notice how, what did we get for the domains? X is less than 5/2. All right, so the domain tells you what part of the graph it'll cover on the x-axis. So notice how it's only graphing over those parts. And x equals 5/2, regardless of whether it's positive or negative, is going to be the vertical asymptote. All right. So with that and transformations, you could graph any log. So those directions are down here. So to graph a log function, draw and label the vertical asymptote. All right, remember, you get that by setting what's inside the parentheses equal to 0. All right, and then this is step 2. Hopefully you don't confuse that with a 0.2. It's 0, end of sentence, step 2. Plot the x-intercept. So that's where y is 0. So you plug in 0 for y and solve, which is usually pretty easy because the log of 1 is always 0. Plot the key point. So figure out like, all right, set it equal to 1, y, and see what x is, and then draw a curve through those points. Once you have the graph, you could state all these things. All right, let's do it. All right, so for this one, graph the log of x base 3. State the domain and range and asymptote. All right, so first, let's find the domain. The domain is going to be, you take whatever's inside the log and set it equal to 0. So that's pretty easy. There's not much we have to do there because it's just x is greater than 0. So that means that when I graph it, I'm going to put my y-axis towards the left because I'm only graphing to the right. All right. And that also means the vertical asymptote is that x is equal to 0. So this is like a border, like the graph cannot cross that border. Okay, then the 2 easiest points that you could find is when like f of x equals 0 or 1. And then you can just solve that. So I'll set the log of x base 3 equal to 0. And we get 3 to the 0 power is equal to 1. So that would be x. So does everyone see what I did there? To find your special points, you just set the expression equal to 0. And then just put it into exponential form. Base, answer, exponent. All right, so now we have the point when x is 1, y is 0. All right, and then do the same thing. Set the whole function equal to 1. All right, so now that means, all right, y is equal to 1. So what's x going to be? Base, answer, exponent. So x is 3. So I have the point 3 comma 1. So we got those 2 points. Now we just connect the dots because it's always going to be just like always increasing or decreasing, and it's going to go through those 2 points. There it is. And don't be afraid to sketch it on your calculator too and make sure it makes sense. Now, for number 2 is pretty closely related to number 1. So everything that we just did, you could do like from scratch and apply that to this question, number 2. But if you know what the log of x base 3 looks like, you could also use transformations to graph this. So this is going to be translated right to, this one. So it's going to be f of x equals the log of x base 3 translated to the right 2. So if we just draw the same y-axis and x-axis, the only transformation that occurred was a translation right 2. So this vertical asymptote is going to move to the right 2. So instead of being at x equals 0, it's now at x equals 2. This point, which was at 1 comma 0, got shifted to the right 2. So now it's at 3 comma 0. This right here is at 3 comma 1. So you shift that to the right 2. That would be at 5 comma 1. So if you know transformations, you can also apply them to logs because they all still work that way. So if you want to look, I'll write this on the top of the page. F of x equals the log, I'll just put b for any base, x minus h plus k. So like h would be translated right h units. So since we were subtracting 2, we moved to the right 2 units. And k would be up k units. Now, for number 1, I skipped over domain and range. Oh, we did domain. Range for any log is going to be all real numbers. Always. So that's nice. For logs, the range is always all real numbers because it goes up and down forever. The domain, all right, well, since the domain here is x equals 0 because of the vertical asymptote at x equals 0, and now it got shifted to the right 2, the domain is going to be x is greater than 2 now because it's everything to the right of 2. But you can also do that by taking x minus 2 and setting it greater to 0 because whatever you take the log of has to be positive. So the domain, get it another way, x is greater than 2. And we got our key points. All right. So for this bottom one here, we could just take the top graph and shift everything down to. So if we plot the same y-axis and x-axis, all right, to compare this to that, well, you can see it on your page. I'm going to run out of room here. But this is just number 1 shifted down 2. So this vertical asymptote is already going up and down forever. So if you move a line that goes up and down forever, up or down, you're not going to notice. But this point, 1 comma 0, that's going to move down 2. So that would be at 1 comma negative 2. And then this point, 3 comma 1, that got moved down 2. So it'd be at 3 comma negative 1. Connect the dots. All right, and the domain for 3 and 1 will be the same because we didn't move it left or right at all. And that's the only thing that would affect the domain. But if you're not sure, just use the fail-safe method. All right, take whatever's inside the log, set it equal to 0, greater than 0. And that's your domain. All right, the range for any log, all real numbers, because it goes up and down forever. And also it's the inverse of exponential. And exponentials have domains that are all real numbers. So logs will have ranges that are all real numbers. Exponentials have ranges restricted by an asymptote. So logs will have domains that are restricted by the asymptote. I keep bringing that up because I think if you understand exponential graphs, logs are just the same thing. You just switch x and y. All right. So let's look at the last type of transformations. All right, so sketch a graph of 2 times the log of 3, of base 3 of x, based off its parent function. So I'll hold its parent function right here. So what that 2 is going to do is it's going to take all the points and take their y coordinates and multiply them by 2, because we're comparing it to like y equals the log of x base 3. So like the original y coordinate is equal to the log of x base 3. So if we were to like multiply both sides by 2, so we take all the y coordinates and multiply it by 2, now we have the graph that we're trying to graph. So we could take like this point 3 comma 1 and take the y coordinate and multiply it by 2, and we get 3 comma 2. Now this point had a y coordinate of 0. So if you double that, that's not going to move anywhere because 0 times 2 is just 0. The vertical asymptote isn't going to be affected because it's x equals 0. So it doesn't, if you take all these y coordinates and double them, they would still be on this line here. So what's going to happen is it's going to get vertically stretched by a factor of 2. So just the shape is going to look different. It's going to get farther away from the x-axis faster. All right. So if you know that this is a vertical stretch by a factor of 2, then you can use that to find the key points. The domain is still x is greater than 0 because we're still taking the log of x, and you can only take the log of positive numbers. The range is still all real numbers because we're just stretching it out. It still is going to hit every y coordinate. And the asymptote is at x equals 0. And you can always find that from the domain by like taking the domain and turning it into an equation. All right, so same idea for number 5. All right, that's going to be a vertical compression of 1/2. So if I put the y-axis and the x-axis in the same spots, all right, the vertical asymptote is not going to change because we're still taking the log of x, and whatever we're taking the log of has to be greater than 0. But these points, all right, you take this point, which is at 3 comma 1, and now we're taking these y coordinates, which were equal to the log of x base 3, and now we're multiplying them by 1/2. So now this point at 3 comma 1 is going to be at 3 comma 1/2. And this point would be at 1 comma 0. So it'll look very similar to the first one we did. It's just going to be like more smushed, more compressed towards the x-axis. All right, so since we're just compressing it, we're not changing the domain. The range is still all real numbers because that's always going to be the case for the logs that we do in this class. And the asymptote is at x equals 0. Okay, Now, the last type of transformation is putting a negative in front of x. So if you think about taking the original parent function, which I'm going to sketch on this graph, all right, it had a vertical asymptote, so you don't have to do this. You can do this green part if you want. But I want to sketch the parent function on the same graph as this. So this point was at 1, 0. I should have made that green. This point was at 3, 1. All right, so this would be y equals the log of x base 3. Now look what's happening from here to here. The only thing that's changed is that we have a negative in front of our x, which means all these points on our original parent function, the x's are going to turn opposite. They're going to become negative. So this point at 1, 0 is now going to be at negative 1, 0. And this point at 3, 1 is going to be at, I wrote that in a terrible spot, is going to be at negative 3, 1. So putting a negative in front of your x is going to reflect it over the y-axis. Because if you remember in geometry, when you took points and changed the sign of x, it would reflect over the y-axis. So the same thing in coordinate geometry, or what we're doing here, graphing on this graph paper. We're taking all the x values and we're negating them, which will reflect it over the y-axis. So we got the key points. The domain now is going to be the opposite of what it was. All right, now we're taking the log of negative x. So negative x has to be greater than 0. So what would I have to do if I was solving for x? If I need to get x alone, I would have to get rid of this negative, right? So you could divide by a negative. But what do I have to do with inequalities when I divide by a negative? Flip the sign. So now we get the same thing that we got before. And you can also just use transformations. Be like, all right, it was to the right of the y-axis. It got reflected. So now it's to the left of the y-axis, where x is less than 0. And that's your domain. And your range, still all real numbers. Asymptote, range, domain. All right. So you can use transformations when you're graphing these, or you could kind of do it from scratch like we did the first time and plot points. Totally up to you. So let's look at this, and I'll get you started on it, and I'll tell you what you could do for the rest of class when you won't have any homework. I think we should get this done in 25 minutes. So let's, it's 20 minutes, sorry. Oh wait, 15, my bad, 15. So let's do the first one together so you know what to expect. And then for the rest of the class, work on this. And then at the end of the class, you can just upload whatever you did. But as long as you're working hard for 15 minutes, that's enough practice with this stuff. So, all right, vertical asymptote. Remember, for the vertical asymptote, you take what's inside the log and set it equal to 0. For the domain, you take what's inside the log and say it's greater than 0. So like domain and vertical asymptote will often look very similar. Just one will have an equal sign, vertical asymptote, because it's an equation of a line. And the other one will have an inequality symbol because it's an infinite set of points that the graph will cover. And the range for literally all of these, you can just write all real numbers. And here, I'll cut your work by 1/3 right now. Ready? Go like this. Bang. Done. Always all real numbers. We don't discriminate against any real numbers. We include all real numbers when we're graphing. Can't say the same about exponentials. They're a little set in their ways, but logs include all real numbers. All right, so yeah, try these, and then we could go over them in like 10 minutes. I'm going to end the recording, though, so that it's not just dead.